Now, so what that tells us, the important thing that we have to consider is that a Brownian motion depends on time, but more importantly, it depends on the square root of the time. Okay, so that means that when we start looking at rates of change or gradients, we end up having a bit of a problem. And the reason is as follows. In everyday differentiation, we have the following. So here's f as a function of x. X is an everyday variable. And we know that if we look at f dashed, then this is, if you look at the definition of the derivative, provided this limit exists, right? So this is fine. F depends on x, so we can look at that particular limiting problem. But what about if you ask, what is f of x, where x is a Brownian motion? Can we also say this? Limit as delta x tends to 0 of f of x plus dx minus f of x over delta big X. The problem really lies here. So whether we say delta x or dx, the problem with this is of size root dt. So order root dt. Now, have you ever seen a situation where when you look at the derivative of something, instead of having delta x tending to 0, it's the square root of the process tending to 0, which is everyday differentiation. So the same can't be done. You can't ask this, because this is in fact dependent on the square root of something. The rate at which the square root of something tends to 0 is very different to the rate at which the actual thing tends to 0. So if you said delta x tending to 0 versus the square root of delta x tending to 0, those are two very different quantities, which means we can't use things like this anymore. We've also seen that Brownian motion doesn't have a derivative. You can't differentiate with respect to t. It's continuous everywhere, it's differentiable nowhere. We saw that in the graph also. But shall we try and argue something similar to that using Brownian motion? Shall we try that? And see what would happen. So let's carry on with that thing at the bottom there. So instead of that, shall we say df by dt? Right, so this is actually, sorry, what I should not say f, let's say x, dx by dt is equal to the limit delta dt tends to 0 of x of t plus dt minus x of t over delta t. So we're going to try and use everyday differentiation rules here. How can we write the numerator? So limit dt tends to 0 of, well, we know that the top is dx, right? That's a change. And this, the top is root delta t, agreed? That's of size the square root of delta t over delta t. What does that become? That becomes 1 over root delta t. So we're saying the limit as delta t tends to 0 of this quantity. Does that exist? So what we've said is we started off with the usual definition of a derivative to work out dx by dt. We found that the numerator is of size dx, clearly, right? but dx behaves like the square root of delta t, or dt. Right? When you simplify this down, you're left with this, and then you ask the question, as the limit delta t tends to 0, what happens to this? So this is essentially telling us that we can't apply the normal rules of differentiation here, because that'll blow up. As delta t becomes smaller and smaller, that doesn't exist. So that means that this kind of calculus won't work here. Are you happy with that? All we've done here really, we haven't done anything flashy other than say, well, let's try and use everyday calculus to see if we can differentiate x with respect to t. But we've seen in its simulation anyway that dx by dt doesn't exist. So let's go back to the notes and see what Paul proposes. Right. Now, what Paul is really doing is saying exactly what we've been talking about. So here's that line. So might we expect something similar in the stochastic world? Well, we said already no. That's not going to work. There we go. We hit a problem because dx is of size root dt, which is bigger than dt. Remember when dt is very, very small, right? This means that we have to be very careful when we work out things like derivatives. So for this reason, in the stochastic world, we instead work with stochastic differential equations. You've already seen a stochastic differential equation with Paul in the very first session. Right? In other words, this. Something times dt plus something times dx. Okay, so these take the form that, where the dot 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 in front of dt, can you remember what this is called? Drift? This one? Is the diffusion. In other words, we can't write down df by dt anymore, right? Which is what you're used to writing down. So what we have to now do is use stochastic differential equations. We know that dx by dt doesn't exist, so we can't write that down. So what we have here is something very, very interesting. We've got something times dt plus something times dx, which behaves like the square root of dt. Now, you don't see that in normal differential equations, where you've got two different scalings. One is dt, so the drift or the mean scales with the time step, whereas the volatility or the diffusion scales with the square root of the time step. So what we're now going to do is we're going to use this idea of forming the derivative. But there's no such thing as a derivative in stochastic calculus like we are used to in normal everyday calculus. So when we say the derivative, we know we're talking about dy by dx. But that doesn't exist here in stochastic calculus. So we look at differentials instead, changes. So can you see, this isn't df by dt or df by something else. This is just df, which is saying the differential in f. And we're going to use this. So just one last thing before we actually go straight into Ito's lemma. What Paul's asking is that what are the rules of calculus? Let's have a quick look. Right. So what he's saying is that normally, suppose you've got a function like this, f is x squared. You would normally say that df is equal to 2x dx. Agreed? Obviously, you take the dx on the other side, so df by dx is equal to 2x. That's everyday calculus. But we've already said we can't use this anymore. We have to use this. Okay, because what that then does is it brings a dt in there. So what are the rules of calculus? And this is what he's going to do. One of the properties of Brownian motion is that as the time steps become smaller and smaller, So suppose we have Brownian motion is dx. If we now square it, so square dx, which we're going to write down as dx squared like that. That is dx times dx. Do not think that this is dx, d of x squared. This is how we write down dx bracket squared. If we square this, and then we take the expected value, this then behaves like dt as the time steps become smaller and smaller. Or another way of writing this down is that the expected value of dx squared is dt. In other words, simulate x, then work out dx, square a whole load of those, take the expected value, and it behaves like dt. In normal everyday calculus, this tends to 0. But in stochastic calculus, it doesn't tend to 0, it behaves like dt. That's the difference between everyday calculus and a stochastic calculus. So what we're going to do is, we're going to take this result and see what happens when we put this in a Taylor series expansion. Right, Taylor series and Ito. So what we're going to do is we're going to go back to basics and see what that tells us about differentiation. So consider a function. X is, let's change this to black, is a Brownian motion. F is equal to f of x, is a function of a Brownian motion. F equals fx is a function of a Brownian motion. Let x change by a small amount. The obvious question to ask is, what happens to f? So, one-dimensional Taylor series expansion. F is a function of x plus dx is equal to f of x plus df by dx times dx plus a half d squared f dx squared times dx squared plus higher order terms. But in everything that we do, we will only go as far as terms in dt. Remember last week when we did the Taylor series expansion, we went as far as delta y squared, but we only went as far as dt, because we're saying that the time steps are becoming so small that anything smaller than dt is negligible. So we're going to do the same here. Now, when we take the f on the other side, that becomes df. That's the differential. So df is equal to this, f of x plus dx minus f of x is equal to df by dx plus a half d squared f by dx squared, and I put a dt there. And that is the most basic form of Ito. In other words, df is equal to, so let me make that equal to a bit more clearer. So there's df by dx times dx, which is everyday differentiation. Then you've got this extra bit on the end coming in, because of the fact that dx squared doesn't tend to 0 like in the normal classic sense, but it tends to dt. So let's see what we get if we differentiate x squared using this formula. So shall we go to a brand new slide? Because remember, df by dx on its own doesn't exist. Doesn't make any sense. So let's go here. So revisiting f is equal to x squared, which we saw before, remember, was df by dx was 2x dx, wasn't it? Everyday differentiation. Sorry, there's an extra dx there, isn't there? There we go. Right, now use, so what we're going to do is, we're going to use this. Where's it gone? All right, so Paul hasn't put that, so shall we just, in red, let's change this to dt. Okay, and apply to f equals x squared. So therefore, df is equal to, well, what's df by dx? If f is equal to x squared, and we want to do this the proper way, df by dx is 2x, and then d squared f by dx squared is 2. So what do we get? We get 2x dx plus a half times 2 times dt. So we end up with df is equal to 2x dx plus dt. Now, if you compare this to everyday differentiation, in everyday differentiation you would only have 2x dx. But because you're now differentiating a function of a Brownian motion, you get this extra term coming in the end, plus dt, which you don't see in everyday differentiation, because that bit there we ignore, don't we? Because it's too small. That goes. I'll let you get this down, and let me just say one other thing, just to clear up any potential confusion there might be. Because when you do normal differentiation, you don't normally think of Taylor series expansions, do you? So let me do that. Let me just come here for a second, and if there are any questions, then you must ask me. Here's everyday differentiation. Look, we have df, so here's f as a function of x. Okay, so f as a function of x, f x plus delta x is equal to f of x plus f dashed x delta x plus a half f double dashed x delta x squared, and so on. But when delta x becomes very, very small, which part of this line would you get rid of? As delta x becomes very, very small, which bit would you get rid of? Any thoughts? But wouldn't it be this? You certainly can't get rid of this, right? So we get rid of this, right? We get rid of that. And let's rearrange this. So everything after this, we ignore. Let's take this to the other side. So f x plus delta x minus f of x is equal to f dashed of x delta x. And we know that delta x is very, very small. Let's divide both sides by delta x. Right? And we've already said that delta x is very, very small. Now, do you recognize that? Do you recognize this formula? That's the definition of the derivative. That's where it comes from. Taylor series is always a starting point for everything. So in Ito's lemma that we just derived, there we didn't get rid of delta x squared. We said delta x squared is actually dt. We can't get rid of it. But anything else is too small. Right? So this formula, which you've always assumed to be the definition of the first derivative, actually comes from here, under the assumption that anything which is delta x squared or smaller, we get rid of. And we've actually got a proper definition. So this isn't really an approximation. This is what we normally use, don't we? If we differentiate from first principles. And what's happened is this formula has now been replaced by the stochastic differential equation, which is written down in terms of a differential now. You can't have things like df by dt. It doesn't make sense because dx dt doesn't exist, which is over here, right? So finally, has Paul written it down at the end? No. So can we just go back to the blank screen over here? And this you will take as your first form of Ito. So let me write that down. So let's call this Ito 1. df is equal to df by dx plus a half d squared f by dx squared times dt. And this is the most basic form. As an example, f is equal to e to the x. So let's obtain the corresponding stochastic differential equation for e to the x. So df by dx is e to the x, as is d squared f by dx squared. So let's substitute it in there. df is e to the x dx, which is normal differentiation, plus you get this extra term coming in. This now is the stochastic differential equation for e to the x. So the kind of question that you might solve is, or the problem you might solve is, given a function, obtain the stochastic differential equation for it. Or, given a function, show that it satisfies a given SDE. And notice that this bit there is the drift, here's the diffusion. Okay, happy with that? Oh no, it's just that sometimes, later on, we'll always write down the something times dt first. It's, remember, the bit in front of the dt is the drift. I just happen to have written it down slightly differently because of the fact that we're doing a mathematical problem. But normally, when you write down a stochastic differential equation, it'll be something times dt plus something times dx. I'll extend this to look at a function of two variables. At the moment, what we're assuming is x is just basically a single variable. Right? We know that embedded inside this is t. But when we talk about f, this is a function of one variable, even though we know that x actually depends on t itself. However, suppose you have a function like this, t squared plus x, or x plus e to the t sine x. That's clearly a function of two different variables, isn't it? X and t. So let's, when we come back from the break, let's look at how to extend this particular formula to handle functions like this. Because here, t is implicit. Over there, t is explicitly present.
It's explicitly present, but it's also part of x.
It's part of x, but x is changing in this, but t isn't really, in a sense. We're saying x goes to x plus dx, right? That's it. But over here, x is changing and t is also changing.
X is also dependent on the change of t.
In this case, no. X then no. The function f is dependent on changes in both x and t. So we're saying that x is changing by a small amount, t is also changing by a small amount. Okay.